Cool. Okay. So last week we went through chapter 1, and we were laying the foundation for your entire chemistry career, okay? Whether that's just the rest of this semester, or this semester plus Gen Chem 2, or through organic chemistry, or through biochemistry, or however far that you need to make it, right? So that was the kind of the foundation there. So fairly important chapter though, huh? Lots of definitions, lots of ideas. And now what we're going to do is spend the rest of the time just kind of expanding on specific ideas, which we kind of touched on here and there in that chapter, all right? And so what we're going to do first is we're going to talk about an atom, and we're going to start to introduce the periodic table too, okay? So if you remember, I think it was maybe the first day that we had class, I said that, you know, part of the challenges of chemistry, especially general chemistry, is that I'm going to be teaching you guys a new language, right? We have math that's involved with everything, but then we have a language of chemistry that's on top of it. And so one of the things that comes along with this language, one of the things that we have to learn how to be able to read is the periodic table, okay? So I know I mentioned it before, but just for everyone's sake, you guys will always have the periodic table on the exams, okay? So that sheet that's posted on Canvas, that says formula sheet, and I can't remember the exact name of it, right? But it's in the modules up at the top, right below the syllabus, right? It says formula equation sheet or something like that. You guys all seen that one? Yes? That is what you're going to be given on exams and quizzes, okay? So anything that's on there, you don't have to memorize, okay? If there's something outside of that that's specific, like for instance, you know, we did a conversion of like pounds to kilograms. Do you guys need to know that? No. Do you guys need to know the metric conversions? Yes, right? That stuff's not on the sheet there, so I do expect you guys to know those, okay? So any of these kind of, do I expect you to know the density of aluminum? Of course not, right? But any kind of equation and stuff are on that sheet. So aside from that, right, you guys need to make the decision on what you need to, what you do or don't need to know. So quick question, I'll get back to this idea of the periodic table, right? How are you guys supposed to know what you do and don't need to know for an exam or a quiz? Where am I going to get your exam and quiz questions from? The textbook, right? So if you're working through those problems in a textbook, you're like, hey, I keep seeing this number used over and over and over and over and over again, right? Like the density of water or something like that. Do you think that's important to know? You guys get what I mean with this? I'm not trying to hide anything from you. I promise I'm not going to, like, you know, pull a rabbit out of my hat here and never show you guys something that you've never seen before, okay? Getting stuff from the textbook, that's all it's going to be. So if you guys want to, you know, have a question about this kind of stuff, come talk to me about it, but remember that I'm not that creative, right? I'm not that creative with my questions. I'm just going to look at the textbook, and that's where I'm going to get it from. Sound good? Okay, so part of that sheet is that you guys have the periodic table on there, right? And so we're going to introduce some of the ideas here first, and then we're going to continue to expand upon that during this semester. Okay? So let's talk a little bit about how we actually build an atom and that kind of stuff. Okay, so atomic theory, I think this is probably something that everyone's, for the most part, familiar with, right? So all atoms of a given element are chemically identical. All matter is made up of extremely small atoms. Now, modern theories, you know, describe the idea of quarks and these muons and gluons and these other things that I forget, right? That's kind of the realm of physics. And so if you go talk to a physics professor and say, what's the fundamental building blocks of matter, they'll have a different answer for you. But for our purposes for this class, you know, we're never going to get really any smaller than what's inside an atom, okay? So that's what we're going to be working with. Compounds form when atoms of two or more elements combine. That's kind of a definition that we had from the chapter, from chapter 1 there. We're going to be talking about this, right? When they combine, they're going to be a ratio of whole numbers. We're going to figure out what that ratio is and what it tells us and how it can come together. And it's all this other kind of information that comes from knowing the chemical formula, okay? Now, I don't want to deceive you all here. It says they usually combine in the ratio of whole numbers. For our purposes, we're pretty much going to stay with whole number ratios. If you step outside a little bit of what we're learning in general chemistry, then you might end up with some of these fractionally occupied materials, right? So, but we're not really going to be dealing with any of that stuff there. So the reason why I use that terminology is just to kind of say, hey, there's some instances where we have a half of an atom inside of a molecule. Now your question might be, well, how in the world does that happen? And that's a good question, right? And so we'll talk about that later on after you get past Gen Chem. So if you guys are going beyond Gen Chem, then we can talk a little bit about that. But for our purposes, whole numbers, okay? Chemical reactions can join, separate, or rearrange atoms. That's where we're going to spend a lot of our time, okay? Bringing things together and breaking things apart. Okay? That's all we're talking about there, okay? And we're going to talk about how can we predict what things come together, how we can predict what things go apart, right? What can join, what can separate, and how we can rearrange things. Okay? But fundamentally, atoms can't be created, right? They can't be destroyed, or can be converted into other types of atoms during a chemical reaction. The only kind of exception with this is when we deal with nuclear chemistry, but if you remember, we're not going to be talking about nuclear chemistry in this class, okay? So for our purposes, a carbon is a carbon is a carbon, right? That's the way it is. It's never going to be anything different than a carbon. It could turn into a different form of carbon, right? More or less bonds, change some electrons, do these kind of things. But a carbon is always going to be a constant force. Make sense? Right? Not too bad then, right? All right, so how do we actually build an element, or an atom itself? I think this is all familiar information for you also. All right, protons, neutrons, and electrons. Those are the three ingredients to make the atom cake, okay? Now, in general, okay, and this is something I'm talking about at the moment with my organic class, electrons are going to be the things that do chemistry for us. Okay? When we're talking about making or breaking bonds, we're going to be looking at how the electrons are transforming, I shouldn't say transforming, how the electrons are moving around, where they're going. Okay? And we're going to talk about that when we learn how to make a bond and how to represent a bond and how to calculate the energy of which bonds are broken and made. Okay? So for the most part, okay, if you want to keep it in the back of your head for the reactions that we're going to learn, it's the electrons that are the things that are doing them. Okay? The protons define which element we're looking at. Okay? And we'll talk about that in just a couple slides here. And the protons, in combination with the electrons, are going to help us to predict the reactions that happen. Because it's not just one or the other. The electrons are doing the chemistry, I agree, but it's also their relationship with how many protons there are, how close they are, how far they are, these kind of things that go with it. Okay? So we can't just point to a single thing in an atom and say this is the most important part of it. Okay? Now, neutrons we're not going to deal too much with outside of this classroom here. I should say this specific lecture here is what I meant to say. That's not to say that they aren't important or aren't relevant. They are, of course, especially if you are interested in the field of medicine. Right? You guys will be dealing with isotopes and radio labeling and these kind of things in there quite a bit. Right? How do we know that a certain chemical gets to the right place in your body? Right? A certain pharmaceutical chemical. Right? So radio labeling is a way that we have of figuring that out. Okay? And that has to deal with the neutrons there. All right, so there's a couple of other kind of maybe important points on here, talking about radiation and radioactivity and neutrons and all that kind of stuff. But for the moment, right, what we need to keep in mind is electrons, protons, and neutrons there, right? That's kind of where we're going to spend the majority of our time, okay? All right, so how do we actually, now that we have the ingredients, how do we bake the cake? How does it come together? Let me zoom out just a bit so that can all come together here, okay? So there are some proposed ideas with how an atom was actually made, okay? So in the beginning, Thomson kind of came up with this idea of a ball of uniform positive charge with small negative dots stuck in it. So this was known as the plum pudding model. So if you imagine, does anyone here ever had plum pudding? I never have. I think this is a term that's kind of fading to iniquity, right? So if you imagine you have a, let's see, what's a more modern context here. So if you imagine you have mint chocolate chip ice cream, right? So you got, I'm not a big ice cream person either, so pardon me, but so imagine you have your ice cream, you have the little chocolate chips kind of stuck around inside of it, right? Just kind of randomly dispersed through there. That was the idea of plum pudding, right? You have basically some fruit that is kind of floating around in a glob of pudding, right? So they basically thought that the electrons and the protons are right next to each other, okay? That's not how it is. Right, but if you take a look at it, right, back in 1910, right, there was an experiment done by Rutherford there to kind of figure out whether this plum pudding mint chocolate chip model was actually correct. And they got some very weird results with it, okay? They expected something to happen, but it didn't. Right? That starts to give them a clue about how an atom is actually put together, okay? In 1912, there, Niels Bohr, one of these famous chemists, which we'll talk quite a bit about, especially when we get to chapter 6. Okay, he came up with a more modern view of what the atom is. So if you take a look at my representations here, I'm kind of walking through the three different representations there, right? So the gray blob there on the left, that's your pudding with the fruit in there, right? The mint chocolate chip with the chocolate chips dispersed, okay? But then in 1910, when they did this experiment, they basically figured out there's a lot of open space in atoms, right? So they said, okay, there's no pudding around anymore, there's no ice cream, right? There's discrete parts of it. And so they theorized that you just have a center part of it, right? And then the electrons are kind of randomly dispersed around it, okay? And then probably on the right-hand side is a model that most of you guys have seen before there, right? Where you have this nucleus that's in the middle, and you see these electrons in defined orbitals rotating around outside of it, right? Very similar to the, let's say, the solar system and how the planets orbit the sun. Right? Is that what you guys have seen before, right? So that's wrong, right? And we'll talk about what it actually looks like. Now, question: would I be showing you guys this stuff here if it wasn't relevant in some way? Well, okay. Am I ever going to ask you what did Rutherford do? No, right? Is the Bohr model 100% correct? No. But is it useful to kind of have a picture of how an atom is laid out? And will the Bohr model help us with that? Absolutely it will, okay? So I want you to keep in mind that it's not that, you know, the Bohr model was thought to be correct for a long time. It's not until very recently in terms of the history of science that we kind of have the modern view of things here, okay? So I don't want you guys to think that, well, you know, my favorite teacher in high school taught me the Bohr model there, and now Dr. H is just telling me that everything is wrong and incorrect. Well, that's not 100% true either. That's not what I'm trying to say, okay? But what we will do is correct kind of how the Bohr model looks into the modern context of things, and why we'll see that it's a pretty good, decent model there to keep in mind, okay? All right, well, we'll talk about that a little bit more as we go forward, okay? Alrighty, so now that we have the protons, neutrons, and electrons, we'll talk a little bit about the different parts of it in here and just how it will relate to what we need to do and how it leads back to the periodic table, okay? So the first couple parts are going to be pointing everything to the periodic table, and then we'll start to read the information off of there is what it is, okay? All right, so when they were going through and they were figuring out, you know, how we can actually build an atom itself, right? They were doing all these tests, and what they found out is that there's just a bunch of mass that they couldn't account for, right? They basically knew there had to be positive things, they knew there had to be negative things, but there was a bunch of other mass that they was unaccounted for, okay? And that's what a neutron is, okay? They're larger than the sum of the protons and the electron masses. So they do make up a significant chunk of the mass of an atom itself, okay? And Rutherford there, who we just mentioned in the previous slide, he proposed the idea of a neutral molecule that didn't have a charge, which is why they were having trouble detecting it, right? So in 1932, right, we started to figure out where neutrons exist, and they were able to kind of calculate the mass of them, okay? And neutrons are present in all atoms with the exception of one isotope of hydrogen, okay? Now we'll talk about what an isotope is here, okay, in just a little bit, but for our purposes, you can assume that neutrons are always around, okay? And I think there's even a slide that we talked very briefly about the isotopes of hydrogen also, okay? But so if you ever see this little N0 thing here, I'm just talking about neutrons, this is what it is, okay? Sound fair? Neutrons, they're big, they're heavy, they're inside the atom, they're in the middle of it in the nucleus, okay? Are they going to do much for us right now? Not really, right? That's the realm of nuclear chemistry, okay? Protons and electrons are going to spend most of our time. Alrighty, we move over to our electrons, our very, very important subatomic particles. Okay, in 1911 is where Millikan first came through and developed a pretty ingenious experiment to figure out how electrons exist and to be able to count them. Now, for any of you guys who are interested in physics and moving on through advanced physics, this is actually an experiment that you guys do in your junior or senior year. So you can actually replicate this in the lab, which I find pretty darn amazing, right? So basically with some oil drops and a good camera, right, in the right setup, you guys can see electrons. And so this guy did it back in 1911. It's pretty crazy. We have trouble seeing electrons with our high-tech equipment that we have today, so you can imagine over 100 years ago what they were working with there, right? So pretty clever setup for experiments, okay? But anyway, what they all did and what they figured out is they were able to kind of suspend some charged particles in between positive and negative ends, and we were able to kind of back out the calculation for an electron there is what Millikan did, okay? So just continuing off of this here, right? So what happened, how did it work, and what does it tell us, right? So I'm not gonna, you don't have to worry too much about like these big numbers that are there, whatever. The point of the experiment that was done is that they found out that there's a particle that has a negative charge, is what it is, okay? Now you guys probably already knew this, we probably already, I'm just covering information that you guys have already known before, right, that electrons have a negative charge. But it wasn't until 1911 that it was proven, is the point that I'm trying to get to, okay? Now, does it really have a -1 charge? No, it doesn't, okay? That's a convention for us, right? The actual value for the charge right there is at -1.6, yada, 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 blah, 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 right? Do I expect you guys to know that exact value right there? Of course not. I will give you something like that, okay? For those kind of constants, I think it's even at the top of the sheet that I was just mentioning at the beginning of class there, okay? The whole point is that it's a negative value. Got it? Now, what we're going to be able to do in the last chapter of Gen Chem 2, so you got a couple of months to go before we get to this, right? What we're going to be able to do is calculate how many electrons get transferred as we make a battery, is what it is. And I think there's an experiment that you guys run in class, in the lab there, where you guys make your own batteries, and you can actually back out the calculation for how many electrons get passed as you guys do a certain experiment there. So pretty cool stuff, right? What I'm saying is we'll talk about coulombs here when we get there. That's what that capital C is. That's not Celsius. I don't think I have to tell you guys that, right? That's not a measure of temperature here, where it's a measure of a charge, and that's what coulombs are, okay? And anyway, so even better from the experiment that Millikan did there, he was able to estimate the mass of these electrons, okay? So 8.96 times 10 to the negative 28. What does that tell you? It's really darn small, right? There's 28 zeros in front of that H right there, right? So 0.0000 blah, 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 right? All the way until you get there. Not a lot of mass, okay? That's the point that's being made, right? So really, really small, right, particle with a negative charge, okay? Now we go in the opposite direction, okay? Atoms gain a positive charge as we knock electrons out of the atom, which isn't that hard to do, okay? In fact, you guys will do something very similar to this in the lab. You guys will get to burn some things, okay? You guys are going to be knocking electrons around, all right? The implications is that there's some fundamental particles that get shuffled around is what they were thinking, okay? And what we found out is that we have these things called protons, right? If you take a look at the charge, right, and the mass and all this kind of stuff, it's pretty much the exact opposite in terms of the charge of an electron, okay? That's the whole point. Life is balanced, right? The good and the bad, the light and the dark, the yin and the yang, right? You guys with me on this? Electrons and protons in balance is where we expect to find things. We don't expect to find charged particles just floating around in space. There's always got to be something there that balances it out. Okay, we're going to talk about that. That's going to be an important concept as we talk about spectator ions. Okay, so there's always going to be things around to balance the charges, right? The load is here, right? The charge is plus, right? So we assume this to be a positive one charge. Okay, good. Electron negative, proton positive. You guys already knew that before I started my whole spiel, right? So I had to I got an hour to talk. I just have to sit here and do this right now, right? Okay, the point being what? The takeaway is that electrons are small, don't have a lot of mass. They're on the outside, okay, kind of orbiting around. Protons much heavier on the inside in the nucleus, but they have the exact same charge, negative versus positive, okay? That's the important takeaway from this. Do you need to know the exact mass of a proton? Of course not, okay? We good on that? Okay, so let's put these ideas together. Let's start to come up with a coherent thing. Let's bake the atom cake. The nucleus contains the protons and the neutrons. We assume that to be at the center of the atom, right? That's kind of our fixed point of origin, right? Whenever you orient yourself, you always have to pick a place that you start, right? Most of the atomic masses of the nucleus, that's kind of what we were saying there with how much do these fundamental particles weigh, okay? The protons and neutrons are way, 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 way heavier than an electron is, okay? It's compact. Well, let's think about this for just a second, okay? Now, you guys know from physics experiments, right? or some other similar experiments. What happens when you put a positive end of a magnet next to another positive end of a magnet? They repel each other, right? What if you do positive next to negative? They attract. Where are all the protons located? In the nucleus, in the middle, in a small compact area. Does that make sense? You guys get what the problem is? You're shoving a bunch of positive things together. Does that make sense? Why don't the protons fly apart? Better yet, you guys just told me that negative is attracted to positive. Why don't the electrons just rush and try and get to the nucleus? Causing all life to cease on the planet, right? Because negative and positive, guess what would happen? A big release of energy, also known as explosion, right? Why don't the electrons just rush to the nucleus? You guys ever thought about that? I'm asking you, have you ever thought about why you exist? Now we're delving into the realm of philosophy a bit, right? Well, why is existence? Why is everything pain? No, I'm just kidding. Right? But that's an interesting question. Why in the world, right, does the nucleus of an atom even stick together? And for any of you guys who are interested in apologetics or these kind of things, right, we talk about the strong and the weak nuclear forces, right, and the fine-tuning of the universe, if you guys have ever heard about these kind of ideas that come out of examining creation and all these kind of things, right? So there are unfortunately, some things that I can't just talk about in the scope of this class, right? But if you are interested in that, I'd be happy to chat with you about it, okay? Just come see me at some point or send me an email, whatever it might be, right? And try not to think about it too much while you're existing, right? I don't mean for you guys to question, whether you're alive or not, right? But the point being, there are some pretty amazing things that make the universe stick together and make the universe exist in the way that it is. That's all I'm pointing everyone towards, okay? But the positive part of the atom is in the middle, okay? The electrons are the small, tiny negative things that kind of float around the nucleus in defined orbitals. Okay? Now, as soon as I say the word orbital, what are you guys imagining? Well, okay, something like the Earth around the sun, right? That's not quite the same thing. What we're going to do in chapter 7 is we're going to learn about how the electrons actually look when they're surrounding the nucleus. Okay? So that image in the top right-hand side there looks kind of like a bunch of different weird-looking spheres kind of tied together, this kind of stuff, right? That's the more modern view of what an atom looks like. Electrons exist in defined orbitals that don't have these nice circular shapes that we might be imagining in our head, okay? But they are orbiting outside the nucleus itself. Sound good? Important things, atoms are neutral, that means electrons are equal to protons. Question, what makes up most of an atom itself? In fact, what makes up most of anything in itself? Do electrons take up a lot of space? No, they're kind of small little things, right? Does the nucleus take up a lot of space? No, it's kind of, as I just told you, it's compact and sitting in the middle there. What makes up most of an atom? Empty space. Got it? Put your hand on your desk. What are you guys touching? Mostly nothing. You guys ever thought about that? Nope. Right? I think I might be a little bit off with my coinage here, but the common view is if you imagine that there is a quarter, right in the middle of a football field, right? Okay, the quarter represents the nucleus. The closest electron would be the size of about a penny, and it'd be in one of the end zones, 50 yards away, right? So that's imagining the smallest atom there. So what does that mean? There's a whole lot of nothing that makes up every atom that you guys are touching. So question, why can we feel things to begin with? Ooh, I suddenly don't like chemistry as much. I'm questioning everything, right? But if most of everything is made up of nothing, but I know you guys don't really believe me, right? Because you're looking at your desk and like, I see things. Well, why do we even see things to begin with? Ooh, all right, I'm done with this. All right, everyone go home. But the whole point is this, right? So we will talk a little bit about what happens as you move atoms close together to each other, right? Right? Don't worry, right? We will be able to explain why you can touch your desk and not phase through it or whatever you want to think about, all right? So, but some interesting stuff to think about there. The atom is mostly made up of empty space, okay? Whole lot of nothing. All right. Okay, So just as a quick this and that, it would be useful for everyone to kind of have a printout or access to a periodic table as we kind of move forward, okay? You guys are going to be needing some information off of that. We're going to have to get familiar with reading the periodic table, okay? I'll go ahead and give you a hint, okay? I know not everyone showed up to class and you're so wait for you guys, okay? On the first exam, you're going to have to read the periodic table, okay? I'm trying to help you. Jeez, what's it going to take to impress you guys, huh? I'm giving you answers to the first exam. You're going to have to know how to read the different symbols. You're going to have to know, right, how to get the atomic weight and how to use it. Got it? So if I'm telling you that, and you have access to the periodic table, right, you should probably get comfortable with reading, right? Does that make sense? That's all I'm really trying to get you guys to do with this. Right? If the first time that you look at a periodic table, as you come to the exam, you're like, all right, I studied for 15 minutes, right, while I was driving over here because I got stuck in traffic on Immokalee, right? So I found some study time there, but don't worry, I feel comfortable doing this. Don't do that, okay? Every exam that you have in this class, you're going to need to use the periodic table in some way. So get comfortable with it. Get familiar with it, know how to work your way around with it. That's all I'm trying to get you to say, okay? Cool. We're going to talk about a couple different things, the atomic number, the symbol, the name, and the weight down there at the bottom. Those are the four main things that we're going to start out with. That is not all the information that's on the periodic table. Not by any means. There's a lot. But that's where we're going to kind of start here for the next couple of slides. Sound good? Cool. All right. So, in brief, let's talk about the names here real quick. You're going to have to know the names of the stuff on the periodic table. Why? Because we're going to have to know how to name compounds, okay? So if I have a compound that's made up of carbon and oxygen, right, we need to know what C and O stand for, okay? We're going to have to know how to name those things. We're going to have to know what the element names are in the periodic table. How are you guys going to get familiar with doing that? Well, most of them you guys probably already know, or at least have heard of, right? I think, who else has a textbook with them? Let me see here real quick. I think the front cover has all that stuff listed out, is it? Yeah, so if you guys open up the front cover of your textbook, there's a periodic table, and the next page right underneath it is where all the element names are listed out, right? So do you have to memorize all those? Should you at least be comfortable with some of the names on those things? Am I going to on the exam give you the most obscure element that you guys have never heard of? Yes, because I am spiteful. Okay, no, I'm just kidding. Right? Just as I know you guys haven't or don't know me all that well, we've only had, what, 3 classes together, right? My view is that, well, just out of curiosity, how many of you guys are biochem majors in here, right? A couple of you guys are, okay? How many of the rest of you, do you want me to close my eyes? I'm going to peek, but I'll close my eyes. How many of the rest of you guys don't really like chemistry and don't want to see it anymore after this? No, I saw it. I'm kidding, right? I know you guys won't raise your hand because you think I am going to come after you. That's not the case at all, okay? I love chemistry. That's why I do what I do, okay? And God's blessed me with a talent to do chemistry, and I'm thankful for that. Okay, and my genuine prayer for everyone in here is that you guys find the same thing that I take enjoyment out of. I'm not saying become a chemist. I'm saying something that you can wake up in the morning and say, boy, do I like this. I am good at it, right? That is a genuine prayer, because I know that's a struggle that a lot of you guys have in here. I'm not going to ask you to raise hands, but the question is, do you guys know what you're going to be doing in 4 years when you graduate from this? Or maybe some of you guys do know what you're going to be doing in 6 months when you graduate, right? It's a tough question. I really hope you guys find an answer for that, okay? And I'm happy to help in whatever way that can be too, right? But what I'm saying is I don't expect everyone in here to become a chemist, okay? So do I need you guys to know what protactinium is or what tennessine is? All these things that we'll never, ever, ever, ever see in everyday life? No. Would I expect you guys to know where magnesium is? Probably, right? That's something that's pretty important to all biological life. Do you know why? That's how photosynthesis works, okay? Magnesium is really important, okay? A lot of you guys have probably taken biology. You guys are going to be talking about photosynthesis. You're going to talk about photosystem 2, okay? Magnesium's involved with that. Probably need to know. Would I expect you guys to know what cobalt is? Is it CO? Is it CB? Is it CT? Is it CL? Cobalt's pretty darn important. Why? Well, there's a couple different enzymes and things in your bodies that work with that. I don't want to know about enzymes, Dr. H. How many of you guys take a multivitamin every day? I do, right? What's vitamin B12? What's in the middle of that? I'll give you a hint. It's Cobalt, got it? Right? So there's a couple of different elements in here that you guys run into in everyday life. And those are the things that I expect. Calcium, magnesium, carbon, right? Yeah.
So our first exam's on September 21st, and like we're supposed to have like little quizzes in between that.
Yep.
Are we also going to know the periodic table for each one?
What do you mean by no?
Like, would there be as much information as there is on like the exams, like equivalent to that?
No. If I'm understanding your question properly?
Like,
What do you
have to know as much? Like, if you have a quiz like Wednesday or something, would we be expected to know the same amount as if it was the exam?
No, look, so the quiz, maybe I can answer, if I don't answer your question with this, then let me know, right? So why do I give you guys quizzes or whatever it might be, right? So part of the reason why I give you guys quizzes is because it's kind of let's say a checkup along the way. Are you guys understanding the major topics that we've talked about so far? For instance, right? I'm probably gonna give you guys a quiz on Friday here, all right? What's one of the major things that we talked about in chapter 1? Just as a thought. Huh? Dimensional analysis and Herd conversion factor. Do you think I'm going to ask you a question about that? Sure. I think I'm going to have this very in-depth question on there that asks about the philosophy of, why does the metric system exist? No, right? What I'm saying is, hey, we talked about this in class. We worked a couple examples, right? Have you been practicing along the way? Do you have the fundamentals down, right? You guys have about, what, a month before the first exam, right? And so that I expect at the exam that you guys will be more familiar with it at that point because you've had a month of practice. Right, a whole month of practice, yes. Now 2 days before practice. He's talking to the guy next to me, I'll do 2 days, right? Does that help answer your question now? Okay, so look, again, I told you guys this, I'll say it again. All of you guys in here can get an A, right? I promise that. I'm not going to look to trick you guys. I'm not saying the questions aren't tricky. I'm taking them out of the book. Some of them are kind of tricky. Okay? The stuff is difficult enough. I don't need to make it any trickier for you. All right? Now, how are you going to get over that kind of anxiety of, oh my gosh, I don't understand anything, and this is tricky, and I feel lost? Well, there's a couple different ways, but the first one is you have to crack open that book. There is no mystery to this. Okay? I know some of us are very familiar with, well, I've never opened a book. I always say this, but I need to like put together you guys have probably seen like blog posts from teachers about like stupid things that students have done. We absolutely talk about you guys. Just so you know. I can't believe my students did this. So I had a student who came by, right? It was, they were failing my class, okay? They had failed 2 out of the 3 exams, right? It was right the day before the 3rd exam, and they came to my office. Dr. H, I really need some help. Can you help me out? Sure, come to my office. Okay. So we're sitting there, I'm trying to work through with them, these kind of things, and they're very lost. I see, I was like, okay, why don't you bring out your textbook, let me show you what it is. So they reach in their backpack, they pull out their textbook, and they pull this saran wrap off of it. Got it? Okay, this is the day before the 3rd exam. They haven't even unshrunk wrapped their textbook. Okay? If I see that's not a recipe for success. Okay? I know I'm asking a lot of your time. I know for those of you guys who aren't going on to be chemists, this might not be your favorite subject. But what I am asking you to do is, I'm here to help you out. And I'm telling you, the first thing you have to do is actually open the textbook and work through it. Okay? That's it. There's no way around it. Right? So we have to do that. So take off the shrink wrap. Sound fair? Get some practice in there. Start with 15 minutes a day. Okay? Put your phone down, put it away. I'm going to work through this stuff for 15 minutes. If that's what it takes, good. If you guys need more time, go to 25 minutes until you get to that point where you feel comfortable doing the material. No big mystery there, right? Sound good? Okay. All right. So, any other questions about exams or quizzes, that kind of thing? Okay. Cool. All right. So back to the elements here then. So in terms of naming, right, let's make sure that we're kind of comfortable with the naming, look through the list a couple times. We will get a lot of practice because we're going to go into the naming here pretty quick, okay? So we're going to have that information. We're going to get a lot of practice along the way too. This is one of the trickiest parts of the first exam. I'm going to ask you guys to name things. I'm going to give you a formula and say translate it into the name. I'm going to give you a name. I'm going to ask you to translate it into the formula. So we're going to learn the rules about how to do that. If you don't know what the elements are called, guess what's going to happen? Missed points. That's not good, right? So guarantee you there's going to be naming on the first exam. Sound good? Okay. Where do the names come from? They're kind of all over the place. If you take a look at one of the most modern periodic tables, we have all 118 elements named now. I think in your textbook, again, let me borrow your textbook here, I don't think they have the most up-to-date periodic table, right? Oh, yes, they do. Okay, never mind. You guys, we got the nice, good textbook there, right? So you see all the way at the bottom right-hand side, you see OG, right, is what it is. Right? I don't even know what the name of that is. I've never dealt with it in my life. We've never talked about it in a single class, any of that kind of stuff. Okay? They're usually named after people or places that discovered it, right, is what it is. Right? How important is that? Maybe, maybe not, right? Everything begins with a capital letter, right? This is important. There's some elements that have just one letter, that's their abbreviation. There's some that have two, right? There used to be some that have three, but we renamed those, is what it is, okay? So capital letter always first, lowercase letter second is what it is, right? Most of the abbreviations are fairly obvious: helium, americium, hydrogen, zinc, all these kind of things. There are some ancient names in there, like gold and silver, lead, tin, tungsten. Tungsten's always a weird one, right? Anyone know the element symbol for tungsten? Yeah. It's W. Where in the world does that come from? It's a German name for it, is what it is. Yeah, do you know?
Wolfram.
There it is, right? So does that make any sense? Nope. You're going to dominate at bar trivia, though. Is that what it is? That was actually a question one time, so when I was doing trivia. So I was proud to say that we won the bar tab that night, too. So my degree finally paid back, right? $10. All right. Anyway, so. Anyway, the point being, there are some oddballs here and there, okay? So just take a look at them, get familiar with them, that kind of thing, all right? Is tungsten an important thing that you guys should probably know? Yeah, right? They're not as common anymore, but where did a whole lot of tungsten used to be used?
Welding. Welding.
Welding, yeah, absolutely. Where else? Yep.
Wait, no, that wasn't tungsten. They did use some in planes.
Probably. Yep.
Was it lights?
Perfect, right? What's the filament of a light bulb? An incandescent light bulb used to be made out of tungsten. So what might that tell us? Well, we'll learn a little bit more about it later, but tungsten's got a really high melting point. Does a light bulb get hot? Would you probably need a metal in there that probably has a really high melting point? Yep, right? But that's kind of gone away now. We've moved to these LED light bulbs, right? That's probably all you can buy unless you go onto Amazon, like the black market of light bulbs. There used to be I don't know, but I know obviously I'm older than you guys are. Did easy bake ovens used to be a thing when you guys were growing up? Right? You guys remember that? Right? They had that light bulb in there and it gave off so much heat you could spend 5 hours baking one cookie, right? Right? So there is a value with moving over to an LED light bulb, right? There's obviously a lot of energy loss that happens with the incandescent light bulbs, and that's kind of the thought behind this here there, right? So, but anyway, tungsten used to be extremely valuable in terms of having lights so you guys could come to class, that kind of thing, right? But anyway, so we have a couple different uses for this stuff along the way. If you guys haven't picked up on it, I'd love to give you guys random trivia around here. Do I expect you guys to know that tungsten's in light bulbs on an exam? No, right? Well, you guys probably remember that? Maybe, I hope so, right? All right. Okay, so what do we have here? So the same element, same number of protons. That's kind of our definition. What makes a carbon? What makes a carbon a carbon? Well, each element is defined by the number of protons, okay? If I have 1 proton, I'm a hydrogen. If I have 2 protons, I'm a helium. If I have 3, I'm a lithium, right? If I have 4, right? 5, 6, 7, 8, all the way up. Okay, that's what defines each element. So accordingly, right, we have a name for that. That's going to be our atomic number. Anytime you see a capital Z, okay, a capital Z, I'm saying, hey, this is your atomic number. Got it? So in a couple of slides, you guys are going to see some Z's. I'm saying that's the atomic number. Good? That's the number of protons. The number of protons define the element. The element is defined by the number of protons. Good? All right, so real quick, this is something we kind of talk about here, and it's useful for our math behind the scenes Practically, we're not gonna see it too much in terms of our calculations. This idea of the AMU, the atomic mass units, okay? This is gonna be a way that we can start to do some conversions from grams to mole, though. This is kind of helping us make some math happen behind the scenes. Now, I'm simplifying things a bit here, right? But I think simple is always a good way to go, right? If you guys want to get more in depth, then come see me in my office. I'll be happy to scare you away from chemistry with too many numbers, right? But to simplify things, the atomic mass unit is a way that we have of relating moles and grams and these kind of information, okay? What is it defined as? Well, an atomic mass unit, the AMU, is 1/12 the mass of a carbon atom, okay? A specific isotope of carbon atom, okay? And so that's where we get that value there from, okay? So if we take our particles, right, our electrons, protons, and neutrons there, right, we have our mass and we can convert it into the AMU, right, and there's our charges here. That's kind of useful for us in some calculations that we're going to be doing, okay? We're going to be calculating the isotopic mass of certain things. That's going to be one of these other tricky questions that are going to be coming up in the first exam. Lots of good information in this class already, right? You know there's going to be naming on the first exam. There's going to be isotopic calculation on the first exam. There's going to be gram to mole conversions, which we haven't talked about yet, okay? So lots of cool stuff that's going to be happening on this chapter here, okay? So, again, not something you guys have to memorize except for this. Do I expect you guys to know that electron 1 minus, proton 1 plus? Yes, okay? I think you guys got that though, right? If not, you guys can tattoo it on your arm or something, be all good. I just didn't do that too. So the mass number, capital A, is the number of protons plus neutrons, okay? Mass number, protons plus neutrons. So the mass number is approximately equal, right? That's what the squiggly equal sign says there, right? To the mass in AMUs, right, for an atom. Now, if we take these ideas and we kind of start to combine them together, right, how can we represent which atoms and we're dealing with and which isotope of the atom that we're dealing with, right? That's what we're going to kind of get into here, all right? There'll be a couple practice problems coming up in just a minute. But for most elements, we have a couple different ways of writing it, okay? So that's what these three methods are here. Let me kind of zoom in on them there, okay? So you guys have heard of carbon dating before, right? We use carbon-14 to date things, that kind of stuff, right? And so when we're dealing with these isotopes and radio elements and the different kind of things, there's a certain way we have of writing the information that we're discussing, okay? So for instance, up at the top, you see the C, you see the 12, you see the 6, right? The C obviously stands for carbon. Those are the element symbols. We get that from the periodic table, right? Good. The 12 is capital A. Capital A is your mass number, which is what? The sum of protons plus neutrons. You guys with me on this? Okay. The 6 at the bottom is what? Z. Z is our atomic number. What is our atomic number? It is the number of protons, which defines the element. You guys with me on this? Good. 6 is always going to be carbon. Carbon is always going to be 6. So is that Z a little bit redundant? Yeah, right? So we can just abbreviate it like this also, right? You guys follow along with that? Right? Carbon always has 6 protons. We don't need to write that 6 down there. Is that 6 information that's on your periodic table? Look at your periodic table real quick. Find carbon. Where is it? I'll give you a hint. It's somewhere between 5 and 7. It's 6. Is that written explicitly on the periodic table? Yes. So do you guys need to memorize that stuff? Do you want to? No? You sure? Come on. You guys have nothing else to do, right? Just a couple. How about 11? You guys want to just memorize it? I'm kidding, right? Do you guys need to memorize the atomic numbers? No. Should you guys be able to identify them on the periodic table? Absolutely. Sound good? Yeah, what's up?
Under the periodic table, they have 2 different series. Do you have to know those 2?
Which ones? Oh, we'll talk about that in just a minute. Whoops, sorry. I tripped over myself there. Right? Now, we can actually, we can write this stuff out too, so sometimes you'll see it written carbon 12, carbon 13, carbon 14, right, just depending on what it might be. Okay? Any of those ways are valid ways of representing what the actual element is. Okay? Sound good? You guys got it? I think we have practice problems coming up next year as well. Yep, yes we do. All right. So there you go. If you guys don't have your periodic table with you, I got it off to the right-hand side for you there. Find me the number of protons, neutrons, and electrons. Very typical book-type question, okay? AKA exam-type question, quiz-type question. Get easy points-type question, right? No way we miss this, I hope. Okay, 3 answers for each. Alrighty, protons in the middle, in the nucleus, small compact region, right? About the same weight as a neutron, positive 1 charge. Defines the number, defines the element, right? So for the top there, what do we have? How can we read the number of protons from the periodic table? What are we looking at? That right there, right? Got it? So that thing at the top of the box. Good? Now, we'll talk about this in just a minute. For our assumption for the problem right now is that these are all neutral molecules. Remember, we can add or remove electrons to make things into ions, which we'll talk about in just a little bit, okay? But right now we have all neutral molecules, which means there's a balance in the force, right? The good, the bad, the dark, the yin and the yang, right, dark and light, that kind of thing. So if I have 29 protons, I have, good, easy stuff, right? How many neutrons do I have? How in the world did we get 34? What is it? There it is, right? So if you take 63, right, minus the number of protons, right? And I assume that you guys did your math right, so that's that right there. Good? Everybody comfortable with that? So if we have 100 questions on the exam, that's all that? Everyone's going to get 100? Some one of you guys will be like, nah, I want to get a 99. Just to throw the curve off, right? Alright. Good? All right. So I will fill in the rest here, just for argument's sake. Protons for magnesium, right, that's coming from there. 12, here is 13, okay. Electrons, 12 and 13, right? And we have, let's see, purple is what I was using. 13 neutrons, and here we have 14 neutrons. Everybody feel comfortable with that? Everybody got the same thing that I did? I have made mistakes before in my math, so always please do double check me on this, okay? What is Cu? Yep, that's copper, right? Copper is right in the, if you look in the middle of the periodic table, the ninth column over, right from that small little inset there on the right-hand side, there's where copper is. Okay? What's Mg? Magnesium. Are you sure it's not manganese? Those are always two very commonly mixed up. Mg is magnesium, Mn is manganese, right? Sound good? Magnesium, very, very, very important. Somebody was talking about welding earlier, okay? Magnesium is used to weld things underwater, right? You can burn it underwater. It's very cool stuff, okay? You guys ever thought about that? How do you burn things underwater? The answer is with magnesium. There you go, right? So if you guys are bored this weekend, there you go, okay? Aluminum, Al, right? Everyone got that? Pretty important. Aluminum everywhere. Just as a quick spiel here and there, again, I'll just dot my trivia in everywhere. Aluminum is one of these things that we should all really make a strong effort for to recycle this stuff. Aluminum is extremely expensive to make energetically, okay? We'll talk about exactly why that is as soon as we get into a couple chapters here, right? But it takes a lot of energy, electricity, to make aluminum into aluminum foil or cans and all these kind of things, right? So before I moved down here, I was in Tennessee, right outside of Knoxville there, in a place called Alcoa, A-L-C-O-A. Anybody ever heard of Alcoa? Well, Alcoa stands for Aluminum Company of America, right? They're this massive aluminum company out there, right? Sits very close to the river. You know why? Takes a lot of water, right? To heat and cool things down and move things along, right? So aluminum's kind of the way that the modern world works, right? Pretty important metal for us all. But so just as a quick this and that, I'm not here to make some giant pitch about you know, your recycling or environmental habits. But aluminum is something important that we should all pay attention to, right? It will really help everyone out if we do that, okay? Okay, cool, done with that, all right. So, now that we know everything there is to know about the basics, let's talk about the actual periodic table itself. Now, the periodic table is randomly arranged, and the way they made it is they just threw stuff at the wall, and it happened to stick in this shape right here. That's pretty cool, right? It's nice and symmetric. You guys get the point that I'm making? Is this random at all? No. Most of the, in my opinion, right, so this is Dr. H's opinion about things. The vast majority of the information comes from looking at where the element is on the periodic table, not necessarily how many protons it has, okay? Where it's arranged on the table. Is it towards the top? Is it towards the bottom? Is it towards the left? Is it towards the right? Is it in the middle? That's going to give us the vast majority of the information that I expect you guys to be able to read on the periodic table, okay? Now, we're not going to talk about all those different properties yet, because otherwise you guys would run screaming out of the room because it'd be way too much for one chapter, okay? But as we move our way through general chemistry, we're going to start to introduce the positioning of different things on the periodic table and why it's so important. Does everyone make sense with that though, right? So we're going to be aiming towards that. There's a little bit of a typo actually found in here the other day, because I gave this spiel to my organic class, and I found out I was actually wrong. So there we go. I've been selling lies for years now, apparently, is what it is. I apologize. There's 91 naturally occurring elements on Earth, right? Do I expect you guys to know that? No. But that's okay. So let me tell you where it came from, and let me tell you about how that's incorrect. So typically, if you take a look, they say that there's 92 naturally occurring elements, hydrogen, all the way down to element 92, which is, anybody have their periodic table open? What's 92? Everyone's favorite. Uranium, okay? Uranium's really darn important. Really, 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 really darn important. You know why? Well, it does a lot of things that you may or may not expect, okay? But one of the interesting things, maybe, again, just a day full of trivia for you guys here, there's actually quite a bit of uranium that can be found in Florida, right? So this might be off by 1 or 2 here, but agriculture is a big thing in Florida, right? Probably not to tell you guys that, and especially in Central Florida, if you guys have ever driven through there. Any of you guys from Florida, native Floridians here? A couple of you guys are, right? Most of you guys are from all around the different parts of the country, right? So if you guys get a chance, drive through Central Florida. For those of you guys who are from here, it's, maybe you can agree with me or not, but some of the most beautiful things, right? So I grew up in the kind of the rolling hillside of North Carolina is what it is, right? So I love these kind of like open places that are in Central Florida there. Actually, the other part, if you don't believe me, it's actually affordable to live in Central Florida. Not so much here towards the coast, right? But anyway, different thing. But so agriculture is a big thing, okay? Tourism is a big thing. Do you know what one of the biggest industries, and there's a lot of it between Tampa and Orlando, what's the third biggest industry aside from government? No. It's phosphate mining. Do you guys know that? Neither did I. Right? But Central Florida's got huge phosphate deposits. Is that important to Florida? Is that important to the country? Absolutely. Right? So phosphate mining is huge. Now, phosphate, which we'll talk about what it is in just a little bit, has a really good friend. You know what it is? It's your good old buddy number 92, which is uranium. Okay? Now, what's interesting is, you guys notice that there's not any basements in Florida. There's a couple reasons for that. One, water, right? The other thing is, there's a buildup of radon that can happen. Okay? Part of the decay process for uranium, the naturally occurring radioactive decay, is that we use off radon gas. Radon gas is towards the bottom right-hand side there. You see that Rn, right? It's number, what is that, 86, right? So it's a really, really dense gas that settles into the basement, right, if you don't take care of it, and it's also radioactive, and so if you breathe it in, it causes all kinds of problems, right? So if you do see some basements, sometimes they have a little fan that kind of sucks air out of the basement just to take care of that kind of stuff, right? So that's a couple of interesting things about what we see here in Florida, right? The 92 naturally occurring elements, all the way up to uranium from hydrogen. One of the man-made ones is right smack dab in the middle of the periodic table. It's our buddy technetium, okay? It's this one right here, okay? Now that's unusual, right? It's sitting surrounded by a bunch of naturally occurring things. Anybody ever eaten any technetium? I have, right? So technetium, I know, thank you, right? That's it. Technetium is used as a contrasting agent for imaging, right? So I was, a couple of years ago, I had some stomach issues. Right, so they're like, okay, we need to take an image of it, drink this grape milkshake. And they lied to me. It tasted nothing like grapes, and it was as far from a milkshake as possible, okay? It tasted like chalk that had a purple color in it, right? So it's kind of like LaCroix, but worse, okay? So anyway, so it's an imaging agent. It's actually pretty toxic, so why'd they make me drink it? I didn't have health insurance, haha, no, I'm just kidding, right? So, no, it was something called colloidal technetium, right? So even if we see some of these things that are toxic, right, we can do certain things and kind of passivate these bad parts of these metals, okay? Down at the bottom there, europium, right in the middle of these two oddball columns that are right here. One of the best contrasting agents that we have, okay? Extremely lethal if it gets loose into your body. Okay? But, you know, chemists are fairly clever at things, so we've been able to kind of harness the powers that we do want out of europium by leaving the toxic sides aside, right? And that's what chemistry is. So the stuff that you guys are learning in here, you may or may not believe me right now, but you're going to be able to explain why europium would be such a good contrasting agent. And if you take some of the organic chemistry classes, you'll be able to say how we can build appropriate contrasting agent to make it safe to put in the human body. Okay? So we got some cool things that we're going to learn. But that's it for today. I will see you guys on Wednesday. You guys have lab this week, yes? Okay, so make sure you guys are keeping up with your lab schedule too.